Hi, my name is Rick and welcome to this presentation about our paper Multi-Loss Weighting with Coefficient of Variations. The work was performed by Cesar Karaoglu, Theo Gevers, Thomas Mensink and I. In general, a loss objective is a linear combination of a set of loss functions, each weighted by a loss weight alpha. Setting different alphas can impact the performance of a model significantly. We wish to find the optimal set of weights for these losses. Classically, this is done by means of an extensive grid search over all the losses, which entail training the model many times. And obviously for modern network architectures, bigger datasets and many different loss functions, retraining many times is not feasible. Consequently, we aim to automatically regress optimal loss weights during training already. Weighting schemes for combining multiple losses have been studied extensively in the context of multitask learning. However, there has been comparatively little research on doing so in a single task multi-loss setting. In this paper, we propose COV weighting, a method that dynamically weights losses throughout training, specifically for a single task multi-loss setting. We hypothesize that a loss term has been satisfied when its variance has decreased towards zero. In other words, this hypothesis says that a loss with a constant value should not be optimized for any further. However, since different losses have different magnitudes, we need a relative measure to compare the variances between them. We use the coefficient of variation as a dimensionless estimate of the variance with respect to the mean of the loss. The coefficient of variation can only be used on a ratio scale. This might not be the case for all the losses that we're using. And as a consequence, we take the loss ratios for each of the losses. This is the current loss over the mean loss, denoting the relative change of the loss in time. We combine the loss ratios and the coefficient of variation to obtain our estimate for the loss weights alpha. To get a bit of a sense for how this would work, we have the following four sets of loss weights for different methods. And in this plot, the methods have each been trained on a depth prediction task on the Cityscape dataset. Each color of a line denotes a different loss. For example, blue lines denote the weight assigned to an L1 loss. It has to be noted that the L1 and SSIM losses are the main reconstruction losses that are able to let the model learn the task. The other two, the LR and DISP losses, are auxiliary losses that refine the prediction. In the left plot, we show the weights learned by COV weighting. It correctly assigns most weight to L1 and SSIM losses throughout training. In the right plot, we show the two baseline methods, multi-objective optimization and Grad-norm. It can be seen that multi-objective optimization assigns all loss weight to DISP losses, which is not what we want. Grad-norm does better, but it assigns low importance to SSIM and LR. And on the next slide, you can see that this actually quite heavily impacts the performance of the model. To do so, look at the first four rows of this table, denoting a loss weight assigned only to one of the four losses. Here you can see that performance varies wildly if you assign high loss weights to one of the single losses. To compare COV weighting to our static weights, please look at the two rows denoting the static weights, the equal weights and the hand-tuned static weights, and compare it to the COV weighting. We can see that COV weighting performs at least on par with hand-tuned weighting. The dynamic weight baselines, uncertainty weighting, Grad-norm and multi-objective optimization all are outperformed by COV weighting, but among themselves vary wildly. To summarize, COV weighting is designed for automated loss weighting, specifically in a single task multi-loss setting. COV weighting makes use of loss statistics during training to automatically weight the relative importance of different losses. It uses the loss ratios to judge how quickly different losses are learned. It then uses the coefficient of variations over these loss ratios to fairly compare it between losses. Experimentally, the proposed method is compared to static and dynamic baselines. From those experiments, we observe that COV weighting outperforms all dynamic baselines, and it performs at least on par with hand-tuned static baselines. For details, please refer to the paper. And to play around with the method yourself, please find our code available on GitHub at the link in this slide. Thank you very much for your time, and if there's any questions, please don't hesitate to reach out to me or any of the co-authors. Thank you, bye.